4.5, last section in Unit 4, concavity, points of inflection, and then second derivative test to determine relative extrema. So we looked at first derivative test for that. Now we're going to back it up with second derivative test. Just some definitions, some ideas. This first whole screen is just giving us an idea when we have something that is concave up and when something is concave down. And I know a lot of times you can tell by looking at it, but there's actually a specific way that we're supposed to be checking, okay? And again, you can take a picture of this, you can write it down, whatever you need to do for yourself. Whenever the tangent lines are below the graph, that's when we know that it's concave upward, okay? Yes, it has a U-ish kind of shape, but not always, right? Sometimes at the ends of a curve, when it's not so obviously U-ish, it's harder to tell. And the best way then to look at it is, where is the tangent line with respect to the curve? And so long as we know where those tangent lines are, we can determine that concavity. Now, the other part that's important here is the slopes of the tangent lines are increasing as you move from left to right. That doesn't necessarily mean they are positive, and this is a point of confusion when we talk about increasing functions versus increasing slopes. It's important to make that distinction. Like when we look at the first derivative test and we see that it's positive, we can say that the function is increasing. What we're talking about here for concavity is that the slopes of the lines are increasing. So they're just getting bigger. They could be, like in this example here, the slope of this tangent line is obviously negative. But as we move to the left, it becomes less and less negative until it becomes 0. Okay, so that's another tangent line. And then it starts becoming more and more positive if we move from left to right. Okay, so that's the idea that you have to keep straight, is that the slopes of the tangent lines are increasing from left to right. That doesn't necessarily mean those slopes are positive. Of course, we have the opposite, right? When we have concave down. Ooh, I added something to this, though. Oh, yeah. So if you notice here, there's the end of the sentence is not here. The slopes of the tangent lines are increasing, which means what? Not yet. Yeah. Sorry, you're right. The second derivative is greater than or equal to 0. Right. The second derivative is greater than or equal to 0. That's so the idea when we look at the first derivative and we see something is positive, then we know the function itself is increasing. When the second derivative is positive, then we know the slopes are increasing. Okay, that's the connection there. That's the parallel, if you will. Not parallel in terms of math, parallel in terms of language. Okay? All right, then we've got the other way, concave down. So in this case, the tangent lines lie above the curve, and they are decreasing. So again, notice here, the slope is positive, but it is becoming less and less positive as we approach this 0, and then it becomes negative and becomes more and more negative as we move along the curve. And so conversely, then the second derivative is negative or 0, non-positive. This is non-negative. When we describe absolute value, that's the way. Those are the phrases we use, non-negative, because it could be 0. That's the way we say. I mean, you could say negative and 0. You could say positive and 0, but the one-word way to say it is non-negative, non-positive. All right, now, from the AB book, again, that's just the concavity test. Now, they don't include the equals 0, right? Because equals 0, we've got that horizontal situation. But if the second derivative is positive, then we should be concave upward on that interval. That's what the I's stand for on that particular interval. And if it's negative, it's concave downward. And then our little workbook, I had to throw this in here because, I don't know, if it works for you, it works for you. So yes, here are the smiley faces, and to Joe's point, Why is, yeah, I think that's what it is. I think, why are these pluses? Because when you're theoretically happy, not just smiling, let's be clear. This is I know they say a smiley face, but it's, in theory, this is a happy face, right? So in theory, if you're happy, then you're feeling positive. If you're frowny and feeling negative, I don't know, whatever. Like, if you don't like it, don't use it. I don't care. Like, for some, you've never seen the smiley and the frowny face before?
Yeah, aren't their faces both the same?
Hey, whatever works for you. If this helps you, use it. If it doesn't help you, ignore it. Okay? If you're better at just memorizing and understanding this without a picture, great. But maybe the picture helps you. If it helps you, great, use it. Okay? All right, moving on. Because now we do need to talk about inflection points. All right? And we alluded to this a second ago. All right? The long story short is that an inflection point is a place where the concavity changes. Right? If it goes from concave up to concave down, or concave down to concave up, that becomes an inflection point. That's just sort of the general idea of what an inflection point is. Okay. It's important that F is continuous there. Okay. A point P on a curve is called an inflection point if F is continuous there, and the curve changes from concave up to concave down, or concave down to concave up. Right? That's where the concavity changes, at that specific point. Now, what's important to understand is that there are some caveats to that. All right. First off, notice here, an inflection point can only occur at a point when the second derivative equals 0. Keyword on can. It is not a guarantee. Just because the second derivative equals 0 does not guarantee that that point is an inflection point. Here's the caveat, right? It can only happen when, it can only potentially become an inflection point when the second derivative equals 0 if the second derivative it doesn't guarantee it. What has to happen, right? The second derivative equaling 0 does not guarantee that the point is an inflection point. How will that point become an inflection point? There's a sign change, right? There's got to be a sign change. And I tried to word it as best I could. It's not great wording, but there has to be a sign change on either side of that point, either side of that x, right? If there's no sign change, then there's no inflection change. There's no inflection point because there's no concavity change. The most commonly used thought of example is the function y equals x cubed, right? There's a place where it looks like it should change, but if you think about it in terms of tangent lines, the tangent lines still are always increasing. The slopes are increasing, sorry. Okay. All right. Yep, we'll leave it. The other part to this that's important is, we made the number lines and we tested those critical values for the first derivative test to determine if a function was increasing or decreasing. The way we determine concavity, the way we determine if something is an inflection point is we're going to make a same kind of number line and look for the sign change that way, and then we can say, okay, yep, this is an inflection point. And obviously this is concave down on this side, concave up on this side because of the value of the second derivative, and therefore we can determine that x value is where the inflection point is going to occur. Right? Good. Example, page 97 in your workbook. I wrote the page down for that. So we're going to determine points of inflection and then discuss, not actually discuss it. It is a little... I wish they wouldn't say it that way because nobody's going to talk about this. You're going to write it down. That's what it really means. So we're going to have a pretty simple example here with this function f. So we're going to look at two examples. The first example that we're going to look at is just this part, okay? Figuring out point of inflection, concavity. Then we're going to apply some of this information to mins and maxes. So this first example, we'll knock this one out. Then the second one will get us the mins and maxes and we'll be good. You guys just want to work through this? You good? Okay. All right. So what we're going to do here is we're going to, first off, we should determine the domain. Are there any restrictions on the domain? No. There's no fractions. There's no negative powers. There are no restrictions on the domain. So I'm going to find first derivative. Okay, so there's my first derivative, 4x cubed plus 3x squared minus 6x. So from there, since we're asking us about points of inflection, I really need the second derivative. So the only way I really found the first derivative is so that we can find the second derivative. Okay, and then at this point, we have to look for those critical values from that to try to determine what might be a point of inflection, okay? And so now I've got my algebra going on here, and we'll get down to that. All right, just to try to make our critical values easier to find. So I factored out a 6, then I factored this, and so I get a 1/2 out of this and a -1 out of that. And then we look at what we call possible points of inflection, okay? And so when I have my 1/2, my x values that I could possibly have, right? I could have 1/2 or I could have -1. And so what we do, this is important. Yeah, we got to say that it's continuous. That's really important to say. That was in the second derivative test, we say that we have to, since they don't give us a specific interval, in this case it's continuous everywhere, and that's a reflection of the idea that the domain is all real numbers. So I can do my test with my number line, all right? And so it's going to look like that, right? From -1, and I'm going to have a 1/2. So obviously, what's the easiest value to test here? 0. So I plug 0 into this, and I get a negative, right? So I know that that's going to be negative. It's one of the things that I've learned, whether it's the first derivative test or second derivative test, when you're doing these number lines, you really do need to test a value in all those regions, because sometimes you'll have some of the same signs there, okay? Over here, I'm going to test 1. 1 is going to give me a positive, okay? So this is, and I know you like to plug them in here too, whichever. For this particular problem, I like just plugging them in here. That's 12 plus 6, 18 minus 6 is 12, so I know that one's good. Here, I went ahead and tested -2, and that ends up being positive. So we have the sign changes at both x values, which means I have a inflection point where x equals -1, and I have an inflection point where x equals 1/2. But since they want the point, you actually have to plug those values into the original function to find the corresponding y or f of x. And then we can talk about concavity, okay? So when I plug those in, just to save a little bit of time, again, this is where we're at, really. -1 comma something, 1/2 comma something. Plug them into the original function, you end up getting -1, -2, and 1/2 7/16. So those are the points of inflection. Then we just have to, the last part is talk about what intervals it's concave up, what intervals it's concave down. And of course, the number line tells us that. So we know that concave, and this is how I say, I kind of put a concave up column and a concave down column. So concave up is wherever we have these positives, okay, and concave down is negative. And so you can write union, you can write and, you can write or. They're not going to ding you for that, okay? So long as you have the intervals correct, and they're not going to ding you for if you put a bracket instead of a parenthesis, it's fine, okay? So from -∞ to -1, and then from 1/2, to -1. Then from 1/2 to positive infinity, that's where I'm concave up. And then I'm concave down between -1 and 1/2, okay? And that's everything for that problem. Questions about it? Yes, Sophia.
I'm so confused. Do you want us to establish that there's like no domain restrictions and then therefore like it's continuous everywhere?
Yes. I think it's going to be important to recognize that because this helps talk about this. You can't have a point of inflection at a hole, at an asymptote, right? And so it's just, you're going to have to watch out for that because sometimes you can still test it, but then you go, wait a minute. That point doesn't even exist on the graph. So how can it be an inflection point? So you have to discount that, okay? So so I would do that. Just watch out for it. All right, other questions? Okay, last example, and now we'll into the Extrema, okay? So here we are given, this is number 6 in your workbook, if you'd rather screenshot it from there. We're given the function f, we're given the second derivative, went ahead and did the work for you, so we don't have to muddle through that. We're wanting to know where the graph is concave up or down and the points of inflection. Okay. This is the second example. This one's a little trickier because of the domain issue that we're going to have here in a second. So we have some issues here, right? Because of the fractions, because of the variables and the fractions, we have some restrictions. So from the original function, okay, what can't x equal? Plus or minus 2. Okay. Right off the bat, the domain cannot equal plus or minus 2, which tells me what about the function? It's not continuous for the whole function is not continuous, okay? And in this case, the second derivative is never equal to 0. Okay? Because of this x squared, right? Doesn't matter what value you put in, this whole top can never be 0, which obviously 10 times some positive number is not going to be 0. So what does this mean? Okay, what does this information tell us? Okay, if there are no quote-unquote critical values that we look at for possible points of inflection, right? Because since the second derivative cannot equal 0, there are no possible points of inflection. Okay, that's what this information tells us. The concavity can still change, but the points of inflection aren't going to exist because of that situation. That's why I wanted to do this problem. Okay, so we can still do. Okay, so so how do we determine concavity, right? So since there are no critical values, possible points of inflection, there are critical values, I shouldn't say that. That's the wrong phrase. There are no possible points of inflection because the second derivative cannot equal 0. We still test on either side of the restricted values because that's where we can look for a concavity change. Okay, so that's what happens when we have a second derivative that can never be 0, when there can't be a point of inflection. There can still be concavity just because there's, like that example number 2 that we looked at for the 4-4 homework. The one graph was concave up, the other one was concave down. All right, but because it was split by an asymptote, there's not a point of inflection. Now there's a point the whole thing was up and the whole thing was down. So we're fine. All right. Now, so here's what that ends up looking like, okay? Long story short is we still use our number line. We're still going to test on either side of those restricted values because that's where we have those vertical tangents, right? We can still discuss concavity. We can still talk about concave up, concave down, and where that exists. We're just, in this particular problem, the points of inflection aren't going to be there. Those are gone. But we can do the rest of it. We already established the top is always going to be what? Positive. It's always going to be positive. So it's the bottom that you have to worry about. And so, because if the bottom ends up being negative, then we're going to put a negative sign here. No, x squared, yeah. Any number you put in here is going to be positive. And so, regardless of the x, whether x is positive or negative, this ends up being positive, which means all of this is positive. So what we have to worry about is when this value is less than 4. Okay, when this x squared is less than 4, then I get a negative value down here. If this value is greater than 4, then this ends up being positive, which means the whole thing is positive. So, all right, long story short, right? Where did I go? Right here. All right, so again, if I test 0, that ends up being negative. Anything bigger than 2, this x squared is going to be bigger than 4, which means this is going to be positive. Anything less than negative 2, this is going to be bigger than 4, so this is going to be positive. So we end up with positive on either side. I picked some values, but you can intuitively figure it out too, just from this idea that when this value, x squared, is bigger than 4, this ends up being positive, and when this value is less than 4, then it ends up being negative. Okay, so in terms of concavity, I set it up the same kind of way. We are concave up from 2 to infinity and from negative infinity to negative 2, and then we are concave down between negative 2 and 2. Okay? All right, let's talk about Extrema before we run out of time. Okay. Extrema, mins and maxes, okay, and how we use the second derivative test to figure that out. So here is the actual second derivative test. Okay, first off, we are saying that the second derivative is continuous near c, whatever c is, whatever that particular x value is. Okay, then the first derivative at c equals 0 in both cases. Okay, so this is where we go. We look at the last problem and go, okay, that wouldn't work for this because it wasn't continuous. Now, we can look at a specific spot where it might be continuous, not necessarily continuous on the whole function. All right. So if the second derivative is positive at that value c, then c is a local or relative minimum. So it works. I don't know if it's intuitively backwards to you. Positive is a minimum, negative is a maximum. To me, that feels a little intuitively backwards, right? But we're not talking about the actual number in the function. We're talking about the second derivative. So when the second derivative is positive, all right, we are concave up, which means, and I visualize it. So if we're concave, I always think of a parabola. That's always my go-to. Okay, concave up, then I've got a U parabola. So the point at the bottom is the minimum, right? When it's concave down, or the second derivative is negative, then I've got an upside down parabola, and I think of the point at the top as a maximum. So if you ever have trouble keeping it straight, because you're like positive minimum and not a maximum, negative is a maximum, not a minimum. If you ever intuitively have difficulty straightening all that out, think about concavity. Think about that parabola. Simple, easy example, and the minimum's at the bottom of the U, the maximum's at the top of the upside down U. Okay? That's the second derivative. That's how I think about it. When I get confused, because we all know we can overthink this stuff. Now, the next piece to this, and this is from our workbook. So you're going to use the first derivative, you're going to find those critical numbers. Right? Those critical numbers, those critical values is establishing this first part. That the derivative equals 0. That's how we find those critical numbers. Then we're going to take those, plug them in, take that x value, plug them into the second derivative, and then we can determine concavity to establish minimum or maximum. Are we good? Can I move from the slide? All right. Last example. This is number 7 there. So you're being asked to find the second derivative test to find relative min-max or local min-max, whichever phrase you like better. I don't care. And we have a function. So give that a shot. Just remember, when we're trying to find the extrema, the minimums and maximums, once we find those critical values, then we're plugging those into the second derivative. And the sign of the value that we get after plugging it in will determine whether it's a minimum or maximum. All right, here we go. So, first derivative, of course, we got to do that first before we can find the second derivative. But we need to find the critical values, right? So, I'm sure I factored out a negative 12x. I did. Okay, so I'm going to get 0, and I'm going to get plus or minus 1 out of this. Okay. wrong thing. Those are my critical values, 0 and plus or minus 1. Then you have to take those critical values and plug them into the second derivative. And if the second derivative is positive, that's going to give you your minimums. If the second derivative is negative, that's going to give you your maximums, right? So, second derivative, I just kind of keep going here. All right, negative 36x squared plus 12. And then I'm going to find the second derivative of negative 1, 0, and 1. Okay, so you take those critical values, plug them into the second derivative, evaluate, and see what you get. So this first one is going to give me negative 24. Second one's going to give me 12. The third one is also going to give me negative 24. Okay? So what does that tell us? Okay? Now, it does ask for the points. So this tells us the x values of the minimums, or minimum and maximums. Okay? Maxima, I guess is the... Okay, so the relative max. So what that means is I plug negative 1 in, so these two are maxes, right? Did I not write that down? I didn't write those down, so I'm going to write those down. So I'm going to have a max that occurs at x equals negative 1, and I'm going to have another one that occurs at 1, because these are both negative. Which means I'm going to have a minimum occurring at x equals 0. Okay? So it's just a matter of plugging those x values in to the original function, finding the y values that correspond, and then I'll have my maximums, relative minimums. So relative max end up being negative 1, 3, and 1, 3. Since I'm taking some to the fourth and then squaring, this negative ends up still just being 1. Okay? And then for my minimum, I'm plugging 0 in. Of course, that's just 0. Okay? Questions on any of that? You guys have done this before. There's a lot to kind of keep straight, right? When we start talking about first derivatives and increasing, decreasing, then we talk about second derivatives being non-negative or positive and 0, or non-positive and 0 and negative, and what that means with respect to the increasing tangent lines or decreasing tangent lines and concavity. There's a lot there, right? And so it's just a matter of keeping it all straight and understanding what it all means and how to apply it all.